everyone, welcome. Thanks for watching. This video is going to be about enthalpy of a reaction. Your first question is probably, what's enthalpy? Enthalpy is the same thing that we've already been talking about when it comes to energy in a reaction. So when I do a reaction in a lab, I can do Q equals mc delta T, find its mass, specific heat, and change in temperature, and find the amount of energy overall absorbed or released by a reaction, so that overall comes in from surroundings or goes out to surroundings when some sort of reaction is happening inside a reaction container. This is just enthalpy, so the heat content in a system, and when we have change in enthalpy, we're measuring how much energy comes out or goes into a system. And so delta is change in enthalpy. And when I'm finding the enthalpy of a reaction, which I indicate with this symbol, it's called a Plimsoll symbol, what that means is I'm trying to find an enthalpy per mole, generally per mole of the thing that's reacting. So let's take a look at this. There's a few different reaction setups I could use to find its enthalpy. Let's focus on this one first. So this is very similar to what you did in the Cheeto lab. We have a reaction happening down here. That reaction is an exothermic reaction. It's releasing energy, and it releases the energy into water. We then use water because water is a convenient thing to measure its temperature. We know its specific heat really easily. We then use water to find the amount of energy. So we're calculating the amount of energy released by the reaction, assuming that that's going to be the same energy absorbed by the water, and that's how we find the enthalpy change. So let's take a look at this. And I want us to keep track of, there's a few assumptions we're going to have to make in order to make our calculations work here. So one thing we assume is that all the energy goes to the water from the thing that's burning. Of course, that's not really true. There's going to be some energy lost as heat, but we're going to need to assume all of the energy went into the water in order to do our calculation. That's okay. We know that that is going to bring up a little bit of error, but that's okay. And then the other assumption that we make is that none of the water evaporates, that we always have, does not evaporate, that we always have 200 grams of water, so that we could plug in our information about water into Q equals mc delta T. So we're going to do Q equals mc delta T for the water because that's the thing measuring our energy. So our information about water I can find here. We had 200 grams, starting ending temperature, and specific heat. Beautiful. Mass of my water, 200 grams. Specific heat is 4.18 joules per gram degree Celsius. Change in temperature is 38 minus 25 degrees Celsius. And we get 10,868 joules of energy. Great. So I found the amount of energy when this amount of ethanol reacts. So when I started with 10.45 grams of ethanol and I'm left with 10, that means 0.45 grams of the ethanol reacted. So that's good to know, I guess. I know how much energy when I have this amount of ethanol reacting, but it doesn't really tell me about the reaction in general. We have a unit in chemistry that's really helpful for comparing things in general, and that unit is moles. So what I need to do is I need to take this amount of energy and put it into per mole of the thing that's reacting. Often when we're doing enthalpy of reactions, we put the energy in terms of per mole of the reactant. Sometimes that varies, but those exceptions we can think about in IB chemistry. So whenever we have a reaction like this, we're always going to put it in terms of per mole of the thing that's reacting, per mole of the thing that you have information about. All right, so I know that 0.45 grams of ethanol reacted. Well, I can figure out how many moles of ethanol that is. And I'll be complete here. The molar mass of ethanol is 46.07 grams. That's something you should be able to calculate. If you're not sure of that, go back to Unit 2. And so we get 0.00977 moles of ethanol. Again, when this much energy reacts when this much ethanol is burned. So now I just want to put this much energy per mole. So I have 10,868 joules of energy per mole of the thing that's reacting, mole of ethanol, which is the thing reacting in this case. And so I get here, and I'm going to put this in terms of kilojoules because my number was very large. So I'm going to divide by 1,000 to get kilojoules. 1112 kilojoules per mole, and I rounded poorly, it should be 1113 kilojoules per mole of ethanol. If you wanted to keep it in terms of joules, it would be 1112641 joules per mole of C2H5OH. And so this is helpful to me because now I can say not just for 0.45 grams of ethanol, this sort of random amount that happened to burn, but for every 1 mole of ethanol, this amount of energy is released. When 1 mole of ethanol burns, it releases 1,113 kilojoules. All right, there's another reaction type that we could do this for, and that's going to be a little similar, but everything's happening in one container. So something like the single replacement reaction here. If I were to think about what this looks like, if I were to think about my reaction container, well, inside my solution here, mostly what I have is water. When I have a solution, the vast majority of molecules in there are water molecules. It's not like I have 1 water molecule or 2 water molecules. The vast majority of stuff is water. Of course, water has IMF. These molecules are also moving. There's lots that we can say about the water. And then we have the molecules that are actually going to do the reaction. So in this case, I have CuSO4, excuse me. And I know that's ionic. Ionic things break up when they're in water. These things are, of course, also moving. And I have zinc that's going to be put into the water. Zinc is a metal, and so in its elemental state, before it's added into the reaction, it's just going to be a metal existing, doing metallic bonding, of course. All right, so the zinc is going to be put into my reaction, and when zinc is added in here, well, these few compounds are going to react. These compounds are going to release energy into their surroundings, just like my reaction over here released energy into its surroundings. In this case, what is it that's surrounding the stuff that's reacting? Well, the stuff surrounding what's reacting is water molecules. So the reaction releases energy into the surrounding water molecules. I'm just going to measure the temperature change in my reaction. So this entire reaction container is going to get hotter because the things reacting release energy into the surrounding water, and then the whole reaction is going to get hotter. And so I'm assuming that I get no heat loss to the environment. All of the heat that comes out of the reaction is going into the water. And that's why I need an insulated container here. This is often called coffee cup calorimetry because it can be done in a styrofoam coffee cup, which is really insulating. All right, so what would this look like? Here's another example. I have my reactants here, and I have some information about my water. And of course, we know the system is dissolved in the water. There's a few more assumptions that we have to make here. Remember, the vast majority of stuff in here is water. yes, I have my aqueous copper sulfate, and then I'm going to put some zinc in there. I'm going to make a new aqueous thing. I'll have some solid copper. But the vast majority of molecules when you have aqueous is water. So I'm going to assume that the specific heat is equal to the specific heat of water. The specific heat for my solution is equal to the specific heat of water. Because yes, there's copper sulfate and zinc, and eventually there will be copper and zinc sulfate, but the vast majority of stuff is water. I'm also going to assume that the density of my solution is equal to the density of water. And the reason that that's important is because if I know the volume of my water, or the volume of my solution here, then I can know its mass. All right. And then my initial temperatures I have here. So just like I said before, I'm assuming there's no heat loss. Okay, great. So I have the situation where I have 25 milliliters here. I'm adding about 10 grams of zinc. And I know a little bit about my two reactants. All right, so to make this reaction work a little bit better, I'm actually going to, there's a point that I want to emphasize, so I'm going to change that amount of zinc a little bit just to really emphasize our point. Let's add, instead of 10 grams, that's kind of a lot, let's just add 0.45 grams. That'll make it a little bit easier to see the process here. So 0.45 grams of zinc. Okay, beautiful. So the first thing I need to do is, of course, just find Q. And to find Q, I'm going to use the information that I'm given here. I have 25 milliliters of solution. I add a tiny amount of zinc, but we're trying to get the amount of energy into the water. So I'm going to use this amount, this information about the solution, knowing the solution is mostly water. So the mass that I use is actually this 25. And I know 25 milliliters, 1 milliliter, 1 gram, using the density of water, is the same as 25 grams. And all of this goes back to the fact that most of what's in a solution is water. So if I'm interested in the energy going into the water, well, I look at the thing that's mostly water, and that's my solution. So don't worry about that amount of zinc that's getting added. All right. Now, specific heat, we already talked about that. We're going to use the specific heat of water. So I have 25 grams specific heat of water because I'm in a solution. The vast majority of stuff in the solution is water. And my temperature change is 73.4 degrees Celsius minus 24.3 degrees Celsius. And I'm going to find a Q. 25 times 4.18 times 73.4 minus 24.3, and I get 5130.95 joules. And that's for these amounts of reactants. All right, so what do I need to do here? Well, I need to find per mole of the thing that reacted. I have amounts for two reactants. I have, get rid of this. Oops. Let's see. Interesting. Okay. So I have amounts for two different reactants. Let's go ahead and delete this and add in another page here. I know about the zinc. I have 0.45 grams of zinc, and I have 25 milliliters of 1 molar, 1 mole per liter CuSO4. And I also know this reaction, CuSO4 plus zinc yields zinc plus copper. Great. Well, I need to find per mole of the thing that actually reacted. Do I know which of these reacted fully? I do not yet. So this is secretly a problem where I have to do limiting reagent to find which of these actually fully reacted. So I'm going to do 45 grams of zinc. Zinc molar mass is 65.38 grams per 1 mole of zinc. I'm going to choose copper as my product. It doesn't matter which product I choose, but I'll choose copper. If all 0.45 grams of zinc were to react, I'm just going to put this in my calculator, I would get 0.00688 moles of copper. Let's do that same thing for CuSO4 times 1,000 mils, 1 liter, 1 liter, 1 mole CuSO4 times 1 mole CuSO4. I need to choose the same product, 1 mole of copper. And so I get 0.025. Clearly, zinc is the limiting reagent here. So then I just need to find the moles of zinc that actually reacted. It's going to look very similar to what we did above, but not finding anything to do with copper. I'm just finding the moles of zinc. And that's going to be 0.00688 moles of zinc. It happens to be the same amount because all of our coefficients here are 1. So I have this amount of energy per mole of something reacted. And I know this amount of energy is released when this many moles of zinc are reacted. So I have 5130.95 joules of energy when 0.00688 moles of zinc reacted. 5130.95 divided by 0.00688. I get 745,778 joules, or to put it in kilojoules, 746 really, kilojoules per every mole of zinc reacted. All right, thanks for watching. Let your teacher know what questions you have. Have a good day.